Welcome to the deep dive. We have an incredibly focused mission today. We are ripping through a stack of sources covering the essential operational core concepts you'd need for the NetSec Analyst exam. Our goal isn't just to memorize answers. It's to really understand the architectural trade-offs and the real-world implications of all these security configurations. We're going for insight, not just facts.
That's right. We're zeroing in on next-generation firewalls,
Mhm.
specifically how they're deployed, how they maintain high availability, and how management scales. We want to give you those crucial nuggets that really illuminate the difference between, say, theoretical textbook knowledge and actual hands-on expertise. We'll be connecting the dots between some basic configurations and what makes up a critical security posture.
And just for context, for those of you who might be aiming for certification, keep in mind this exam is typically a 90-minute gauntlet. You're looking at maybe 60 to 75 questions. You'll see multiple choice, scenario-based stuff, some matching sections.
And it's usually administered via Pearson VWE, running around, what, $250 USD?
Something like that. But today, we are skipping the test prep fluff and diving straight into the network foundation. So let's start with a classic deployment challenge. Imagine you inherit a network, and management mandates you have to insert a new firewall for inspection. The constraint is absolute. You cannot modify any existing routing tables, you can't touch any IP addresses, and you can't change any switch VLAN configurations. You have to be an invisible bump in the wire.
What specific interface technology solves this operational nightmare?
Okay, yeah. The key solution here is the virtual wire interface. It's elegant because it achieves absolute transparency. Operationally, you're just connecting two layer 2 segments, and the firewall simply bridges them. The crucial nugget for you to understand is that it completely bypasses the need for the firewall to participate in, layer 3 routing.
So it literally acts like a very smart, transparent
Cable. Precisely. It doesn't consume an IP address on those segments. It doesn't modify the hop count in any existing network paths.
That doesn't do ARP or anything. No, it doesn't participate in ARP, Address Resolution Protocol. And this is absolutely critical for environments where latency is everything, or where you just don't have the administrative window to re-engineer the core network architecture. It's the highest impact, lowest disruption way to drop a security device in line.
That transparency is fascinating. Now let's talk resilience. So moving from a single invisible firewall to a pair of them, we need high availability, specifically an active-passive pair that can fail over without dropping user sessions. For that seamless transition to happen, what are the two absolutely mandatory, non-negotiable link types needed between the HA peers?
Right. You need two dedicated, separate communication paths, and they serve entirely different functions. The mandatory links are the HA1 control link and the HA2 data link.
Okay, so control and data, that seems intuitive, but let's dive into what makes those functions so distinctly separate that they require their own cables. What's the risk if these functions are merged or if one link fails?
Well, if we connect this to the bigger picture of system stability, the HA1 control link is the lifeline. It's the system heartbeat. It handles all the configuration synchronization, making sure the passive device always mirrors the active one, and it exchanges those critical heartbeat and health check messages.
So if HA1 fails...
If HA1 fails, the devices can enter a split brain scenario. They just lose their fundamental awareness of each other's operational status. It's bad news.
And the HA2 link, that's where the high-stakes work happens, I'm guessing.
Exactly. The HA2 data link is what allows the firewall pair to ensure continuity. It is responsible for transferring the real-time session tables and runtime state information. So think about a long-established SSH session or a massive file download. When the active device fails, the HA2 link has already prepared the passive device by transferring that session state.
Ah, so without it, everything just drops.
Everything drops. If HA2 is missing or fails, the firewall might still fail over. But every single active user session will immediately be terminated because the new active device has no record of the connection.
That makes the separation of duties, sync versus state transfer, absolutely essential.
Okay, so we have a resilient deployment. Let's look at external access. An administrator needs to take traffic coming from the outside, the untrusted internet interface, and forward it to a specific internal private web server. What type of network address translation, or NAT, is needed to facilitate this inbound traffic flow?
This is classic inbound connectivity. Destination NAT, or DNAT. The term tells you exactly what's being translated, the destination IP address. The firewall takes the public IP address that the external user targeted and translates it to the internal non-routable private IP address of the web server.
And this is distinct from source NAT, SNAT, which we'd use for our internal users trying to get out to the internet, right?
Absolutely. SNAT translates the internal source IP to a public one when internal users go out. DNAT just flips the script. It is the crucial gatekeeper for inbound connections. It keeps your internal network topology hidden. Okay, so we've focused on external users, but security is often about protecting the device itself from internal users, specifically administrators and auditors. Let's tackle role-based access control. If you need to create a role for an auditor, someone who needs maximum transparency, capable of seeing every log, every configuration detail, but who must be prevented from making zero changes, what specific system role do you need?
This is a perfect enforcement of the principle of least privilege, specifically tailored for auditing. You need the global read-only administrator role.
That seems straightforward, but let me introduce some friction here. If the global read-only admin can see everything, certificates, security rules, the full config, doesn't that itself present a bit of an insider threat risk?
That's a great question, and it's why separation of duties is so key. The technical answer is that while the read-only admin has high visibility, the system enforces the block on all modification. They can't elevate privilege, delete logs, or change a rule. But you're right, the visibility itself carries risk. If they have access to sensitive info, like credentials hidden in service objects or network topology details, that information needs to be protected by other means. Strong two-factor auth for management access, strict physical access control. The role is really designed for compliance visibility, and the organization has to manage the trust around that specific user.
Okay, moving to the modern network edge, remote access. Global Protect VPNs are critical for the remote workforce. What two core components are absolutely mandatory for a deployment to function correctly, letting users connect and maintain their configuration?
You need a blend of user management and session termination. So you need the Global Protect portal and the Global Protect gateway.
What's the division of labor there? Why can't one component do both jobs?
The portal is the management brain. It's responsible for supplying the configuration instructions, the security policies, and even the Global Protect client software itself to the remote users. Think of it as the registration desk.
Okay, so it tells the user where to go and what rules to follow.
Exactly. The gateway, on the other hand, is the connectivity muscle. It's the actual connection point, the network interface, that terminates the user's encrypted VPN session and applies the policies to the traffic. If you just have a portal, users know the rules but have nowhere to connect. If you just have a gateway, users can't get the config or software to even start the connection.
That separation makes perfect sense. Okay, let's scale up. We're managing dozens of firewalls using Panorama, the centralized management platform. When we want to ensure configuration consistency across all these devices, specifically foundational network settings, what specific configuration type is managed by templates?
Templates are strictly for device-level configuration. This covers critical settings like network interfaces, so IP addresses, subnets, link status, and also zone configurations, the security boundaries we define. By pushing these foundational settings via templates, you guarantee that every managed firewall speaks the same network language, which is essential for routing and policy.
So templates handle the network plumbing, which begs the question, why is it mandatory that security rules and address objects are not included in templates? What operational disaster are we trying to prevent by separating them into what's called a device group?
That separation is critical. If you put security rules into a template, every device that inherits that template would have the exact same security policy. This is operationally impossible in most large organizations where devices serve different functions, like a DMZ or internal segmentation or edge security. Each needs unique rules.
I see.
Templates enforce consistency for interfaces. Device groups enforce uniqueness and segmentation for policy. Mixing them would create an unmanageable mess.
That makes perfect sense. Let's switch to another real-world snag. By default, the firewall uses its dedicated management or MGT interface for all its admin traffic, fetching licenses, doing cloud updates, critical DNS queries. But what if that MGT interface is isolated and doesn't have a route to the internet? How do we overcome this isolation to allow the firewall to reach external services using a standard data plane port?
Yeah. We use the service route configuration. This feature is an override. If the MGT interface can't fulfill its duties, and it's often isolated by design for security reasons, separating the control plane from the data plane, the service route lets you tell the firewall. For specific services, like license activation or DNS, use this defined beta port and its routing table instead.
So it's essentially telling the firewall to use a front door traffic port to run its administrative errands rather than the isolated backdoor management port.
Exactly. It's an essential tool when you're dealing with highly segmented, secure network designs.
Okay, here's where we get into the guts of security inspection. An analyst is reviewing the traffic logs. They see a user session, but instead of seeing a recognizable application like Office 365 or YouTube, the application field just says SSL. This is a huge security visibility fail. Why is the firewall blind, only seeing the generic encrypted layer?
This is the definitive aha moment in firewall management. Decryption is not enabled for that traffic. When the log shows SSL, it means the firewall did its initial packet inspection. It knows the traffic is encrypted, and it usually knows the destination port, like 443, and the certificate details.
But why is knowing the port and the certificate not enough for App ID?
Because App ID needs to look inside the encrypted payload to identify the true application signature, the behavioral pattern that says, this is Slack or this is Netflix. If you don't have decryption enabled, the App ID function is defeated. And more importantly, if App ID is defeated, all the other critical security profiles, threat prevention, vulnerability protection, antivirus, they can't inspect the content.
So you're letting traffic through completely blind.
Completely blind. The risk isn't just identification. The risk is malware riding inside that SSL tunnel, totally unchecked.
That perfectly illustrates why decryption is mandatory. Okay, let's move to file control. We want to implement a policy to stop high-risk executable file types, think .exe, .bat, or .vbs, from being downloaded or uploaded anywhere on the network. What specific security profile handles file type enforcement, regardless of whether the traffic is HTTP, FTP, or something else?
This specific enforcement is handled by the file blocking profile.
Why isn't this handled by the antivirus profile? Aren't we looking for malicious content?
That distinction is crucial. The antivirus profile looks for known malicious signatures inside files. The file blocking profile, however, controls the transfer of files purely based on their type. We block .exe files not because we know they're malicious, we block them because their capability is high risk and it violates policy. We want to prevent the distribution of potentially risky executables, known or unknown.
So it's about policy, not detection.
Exactly. You use file blocking to enforce policy, you use antivirus to detect threats.
Excellent clarification. Okay, final operational question, which touches on our earlier point about visibility. Which specific security policy action allows traffic to pass freely through the firewall, but, by default, specifically ensures the session is not logged upon closure?
The action is simply allow.
Wait, just allow? I thought all successful traffic was logged. If the policy action is allow, doesn't that inherently mean allow and log?
This is a point of frequent confusion, and it's where security analysts often make mistakes that blind them. The allow action only grants permission for the traffic flow. Logging is a separate setting within the policy rule. It's a checkbox that has to be explicitly enabled, usually at session end. If the administrator uses the allow action and fails to check that box, the traffic flows perfectly, but no end-of-session log is generated. The connection occurs silently.
The silent allowance, that is a huge operational vulnerability.
Absolutely. It means the system is working exactly as configured, but the administrator failed to configure visibility. That traffic is completely invisible to any forensic analysis.
Thanks for joining us on this deep dive into network security fundamentals. Keep seeking those surprising facts.